All right, Physics 210 students, welcome to a super fast review of Chapter 16 to get you ready for that final exam. We're going to crack the code on waves.
Look, I know finals prep can be a grind, so this isn't going to be some long, dry lecture. Think of this as your strategic guide. We're going to focus on the types of questions you're actually going to see and exactly what you need to know to nail them.
So here's our game plan. We'll start with the anatomy of a wave, then get into what happens when waves collide. After that, we'll look at standing waves, solve a classic harmonics problem, and then I'll give you a simple game plan for the exam itself.
Okay, first up, let's look at the absolute blueprint for pretty much any sinusoidal wave problem you're going to face. If you get this equation, you are well on your way. You open your exam and you see something like this. It can look a little intimidating, right? But I promise you, all the information you need to solve it is sitting right there in front of you. The trick is just knowing what all those symbols mean.
This right here, this is your master formula. It's basically the DNA of a wave. It tells you everything you need to know about its position and its motion through space and time.
So you see, the equation itself just hands you the wave's most important properties. In that problem we just saw, the amplitude, Ym, is that 2.0 centimeters out front, the angular wave number, k, is 2.0, and the angular frequency, omega, is 4.0. They just give them to you.
Here's the easiest way to keep k and omega straight. Just think of k as being about space. It's related to the wavelength, right? How stretched out is the wave? And omega is about time. It's related to the period. How fast is it oscillating up and down? One is space, one is time.
So how do we solve our problem and find the speed? Well, the formula is beautifully simple. It's just omega divided by k. We grab our values from the problem, that's 4.0 divided by 2.0, which gives us 2.0 meters per second. That's it. It really is that straightforward. But, and this is a huge but, you have to remember this. For a wave on something physical, like a string, the speed is also set by the properties of that medium. So the first formula, v equals omega over k, describes the wave's motion. This formula here, with tension and mass density, explains why the wave has that speed to begin with. You crank up the tension, you get a faster wave.
Okay, so we've got a handle on single waves. Now let's make things more interesting. What happens when two waves try to occupy the same spot at the same time? This is where we get into superposition.
It sounds really fancy, right? Principle of superposition. But all it really means is that waves add up. They don't bounce off each other like billiard balls. They just pass right through each other, and for the moment they overlap, their heights just combine.
And this leads to two really cool outcomes. If the waves are perfectly in sync, a peak meeting a peak, they build each other up. We call that constructive interference. But if they're perfectly out of sync, a peak meeting a trough, they cancel each other out, and that's destructive interference. And of course, physics gives us a beautiful little equation to describe this perfectly. When two identical waves meet, the new amplitude depends entirely on that phase difference, phi. If phi is 0, they're in sync. The cosine of 0 is 1, so the amplitude just doubles. Makes sense. If phi is pi, they're out of sync. The cosine of pi over 2 is 0, and the whole amplitude vanishes. Now let's look at a really amazing special case of interference. This is what happens when you create a wave pattern that looks like it's not traveling at all. It just seems to be vibrating in place. And this is fundamental to how musical instruments work. So how do you get one of these? Well, imagine sending a wave down a guitar string. It hits the end, it reflects back, and it starts interfering with all the new waves you're sending down. If you get the frequency just right, you create this stable pattern, a standing wave. And the key here is that energy isn't flowing down the string anymore. It's trapped in these little oscillating pockets. Every single standing wave has these signature features. You get these points called nodes where there's total destructive interference. They don't move at all. And then you get antinodes, which are points of maximum constructive interference where the string is whipping back and forth. And here's a crucial fact for your exam. The distance between one node and the very next node is always exactly half a wavelength.
So let's use what we know to solve a very common type of exam problem, figuring out which specific wavelengths are actually allowed to exist as standing waves on a string of a certain length.
Okay, this question is all about understanding what we call boundary conditions. The setup of the string, one end fixed, one end free, creates a set of rules. For a standing wave to form, a fixed end must be a node because it can't move, and a free end must be an antinode because that's where the motion is greatest. So check out the pattern here.
For this weird string with one free end, the absolute simplest standing wave that can fit is just the first quarter of a full wavelength. See that? The next one that works has to fit 3/4 of a wavelength, and then 5/4. It has to be an odd number of quarter wavelengths to satisfy those rules.
So how do we solve our problem? Well, it tells us the string is in its fundamental mode. That's our cue. That's the n=1 case. We know that for this mode, the length of the string, L, is equal to 1/4 of the total wavelength. So if the string is 40 centimeters long, the full wavelength has to be 4 times that, which is 160 centimeters.
Now please, be careful not to mix up the boundary conditions. The case you'll see most often is a string fixed at both ends, like on a guitar or a piano. The rules are different there. For that setup, the allowed wavelengths are lambda equals 2L divided by n, which leads to this formula for the resonant frequencies, or harmonics.
All right, we have covered a lot of ground. So let's just boil it all down into a simple, repeatable strategy you can use for any wave problem they throw at you on the final.
Here it is, your 3-step game plan. First, just identify the situation. What are you looking at? A single wave? Interference? A standing wave? Step 2, be a detective. Go through the problem and pull out every single number and variable they give you. And step 3, pick the right tool for the job. Match the formula to the situation you identified in step 1. Do this every time and you'll be golden.
You know, what we've talked about today goes way beyond your physics final. Because when these waves travel through the air and hit your eardrum, well, that's sound. The principles are the same. This is the foundation for understanding so much about our world. Good luck with your studies. You've got this.